Okay, I have one or two physics videos. So if you want, you can go to our YouTube channel. Okay, I can show you how my thumbnail looks like. What? Channel. Video. Okay, physics, O-level physics stuff, videos. Haven't come out yet. Huh? Which one is it? If prelim paper 1 day, 1 week. I always have a problem navigating your channel, YouTube Studio. Physics. There? No, e-maths. E-maths. Okay, why I chose this one? This one chosen by the I think it's a last year when I did Sec 3, you saw this one. Where are they? Okay, never mind, like there's somewhere there, right? So because we got too many videos. So, where is it? Can I search? Energy for motor. Let's see what we talk about inside. Never come out yet. Schedule. Where's the schedule? What? What is this? Okay, let's put it up now. Is it now? No, it's say, can I like just public now? Oh, yay. Yeah, it's public now, right? So you can go and watch, okay? The kind of stuff we do. Oh man, so totally unedited. Okay. Wait, is it even ours? Shit. No, what is this? What is this? No, I think this is Sec 1. This is like Sec 1. No, this is Sec 1. Wrong label. Okay, so I gotta hide again. This is a wrong thumbnail, wrong labeling. Okay, sorry, we really got too much, right? Done. So I don't know where is the physics stuff. And I just recorded all this here. Sec 1. Physics. Yeah, the heck. Thumbnail. Change. Save. Never mind, unlisted. So I haven't checked. Right. As you can see, I don't do everything, okay? So I better check everything now. Right, it's somewhere there, right? I just don't know where is it. Sec 3. Okay. 2019 one. Okay, you can go and watch. Yeah, so this one is Sec 3, right? So we do have, okay, it's somewhere inside. In the month of May, we have one every day. So, but it's all over the place, okay? So anyway, let's continue. Like you want to go and watch a video, like you want to find out, right? You can always go and YouTube and go and find like kinetic model or physics or electricity or what, right? Everything's there. Okay. So right, so we're going to go through this chapter. It's called the kinetic model of matter. Now, what is this kinetic model of matter? Let me just draw 3 boxes first to explain. 1, 2, 3. So we have the first one, solid. Actually, I should just go and search kinetic. Okay, this one. Okay, just look at that. So solid liquid gases. Okay, have you all gone through something like that before? Sec 2? Yeah, right. Yeah, right. Okay, so solid liquid gases. Now, the solids, they are closely packed in an orderly arrangement like that. Then liquids are inorderly, disorderly arrangements, but they are also pretty closely packed. So they are gases is disorderly arrangement, but they are not closely packed, they're just far away. So these are the arrangement of particles. Now, how about the energy level? So in terms of energy level, this guy has got least energy, this one quite a bit, and this has the most. And the force of attraction between the particles is very strong. This is somewhat strong, and this is the no force of attraction. So this is how we describe the outlook of the particles in solid liquid gas. Now, how about the movement? Movement itself. So movement of particles for solids, right? They vibrate on the spot. For liquid, it's sliding against one another, and then for gases, they're just flying everywhere. So because of this movement, the movement is actually derived from the energy level that is found in the particles. So you can see here, this has a least energy. So because they don't have so much energy, they're just vibrating about a fixed position. Liquids that have like moderate amount, so that's why they're moving by sliding against one another. And gases has the most, that's why they're flying everywhere. So the most commonly asked kind of question is the processes, like what is melting? Okay, melting. Okay, here's a pretty cool one. Yeah. All right. Okay, so what is melting? You see, melting is from solid to liquid. So how does the particle change from this type to this type? It has to gain heat, right? So when the particles gain heat, what happens? They increase. Okay, you can see here, increase in temperature. Then after that will be increase in kinetic energy. So that's why this chapter is called kinetic particle theory, right? It's about the movement of the particles. So this thing gains heat, it moves faster. Now once it moves until a certain amount of energy, it's able to break the strong force of attraction, it will become the liquid state. And at the liquid state, it will start to be sliding against one another. Likewise, from the liquid state to gaseous state, it also has to absorb enough energy to be able to change, to break the forces of attraction here into the gaseous state. So is there any other state after that? No more, right? So on Earth at least, we only have 3 states of matter: solid, liquid, gas. Now some people say there's a 4th state. Any idea? Hmm? No. Aqueous is dissolved. What's the 4th state? Any idea? No? It's called plasma. Plasma. I don't know what kind of plasma. Plasma. They say plasma has a 4th state. Okay, not I invent one, it's people say one. Plasma is called the 4th state. Right? Just as a liquid ball, blah, blah, blah. So there's actually a plasma, like a plasma state. Okay, where is plasma? Solid, liquid, gas. You keep adding heat to gas, it becomes plasma. That's not how, I don't know if that's related to plasma TV, okay? I have no idea. I know plasma, right? But plasma, honestly, I'm not sure. Yeah, I haven't studied this before. Okay, but according to the diagram, what is this plasma? Nucleus and electron, right? You see, you split the electron and the nucleus, and then they just no more atom. Like even the atom is gone. Okay, so you only have the electron and the proton and nucleus flying around everywhere. Okay, so that's they say one, right? So you don't have to bother about that because you only study 3, solid, liquid, gas. Okay, so one thing they like to test, of course, is moving forward and moving backwards. So moving forward will be gain heat, moving backwards will be lose heat, right? Then there's one strange phenomenon, it's called sublimation. Okay, do you know what is sublimation? Huh? Solid to gas. Solid to gas. So what changes from solid to gas? Do you know what are the things that change from solid to gas? Dry ice, very good. Oh, well, you can buy dry ice. Okay, so dry ice. This is dry ice. So you see during weddings, dry ice during wedding. Okay, people like to put, oh, this is a bit too much, right? So they put the dry ice. So why dry ice? Reason very simple, because there's no liquid. No liquid, huh? What's the meaning of no liquid? That means the dry ice skipped from solid to gas, no liquid state. Okay, why no liquid state? Reason very simple. It's because the melting point and the boiling point is very close. For example, let's find out what is the melting and boiling point of dry ice. I don't know how to convert it. 69.9 melting and boiling point. Sublimes. Isn't that like degrees Celsius? No simple information. Okay, so basically the idea is very close here and here very close. Melting point and boiling point very close. Okay, so what happens is once it comes to the room temperature, instead of going to the liquid state, it jumps straight to the gaseous state. Yes, and so unlike water, you see water here 0, here 100, right? So there's a gap of 100, right? Right. So but dry ice is not so big. Okay, so you don't get to see like the liquid state, right? Jump straight to the gaseous state like that. So they like to use this because you don't want the whole place to be wet, you know what I mean? After a while, you have the effects already, right? Then, oh, can you imagine the whole place is wet? So that would be terrible. But what's happening here is that you're releasing a large amount of carbon dioxide into the air, right? So all this carbon dioxide, the dry ice, it goes into the air, which is supposedly bad for health, right? But that's like too much. Okay, so don't put too much. It's a bit is fine. Okay, this one is like a little too much. Wow, this one is, yeah. So this is dry ice. So that's sublimation. Now, is there any other thing that sublimes from dry ice that you can think of? Goes directly to the gaseous state during in a room temperature. M O T. Any idea? Cannot give a. Hey, is that really? Sorry. More. You can read my mind. Okay. So more balls also sublime from solid to gaseous. Okay, where do we see this? Toilet bowl, right? Toilet, toilet bowl, there's a lot. So why do we want them to sublime into gaseous state? Now, why do people put this inside toilet bowl? Toilet bowl, not toilet bowl, urinals. Okay, why? It's so that they can mask the smell of urine. So your toilet smells clean. I say smells clean, okay? But is it really clean? No. Why? Now, when you put this thing in the urinal, of course, let's take a look. Ew, look at that. All right, so people throw them inside urinals, okay? So when the human being pee inside, they pee. So here now it's still solid, right? Solid, huh? Human body, what temperature? 36.9. Do you know? Don't know. Okay, 36 something, right? What's room temperature? Maybe 30, right? 30 or 28 or 30, right? So when the pee come inside, mix with this thing changes from solid to gas. You got it? So what happens is that you go in and then you pee on it, and then then you take a deep breath. Smells pretty nice, right? You smell mothball, correct? And then all of a sudden it's like, hey, this toilet not bad, it's quite clean, right? No urine smell, right? But is it true that there's no urine smell? No, it's not true. It's because what happens is that these mothball particles is so overpowering, they mask the urine smell. You get it? So the toilet smells nice now. Not because got no urine particles in the vapor, but because there are more mothball particles than urine particles. How come more mothball particles? Because they become gas. The chemical become gas. So to me, it's actually even worse. Why? Because now not only do you breathe in the urine, you also breathe in mothball. Can you imagine you breathe mothball into your lungs? You're breathing mothball in your lungs. Oh, it smells so nice, right? It's actually chemical going inside. This thing goes in together with the urine. Okay. Same for what do you call it? The deodorant stick. Have you seen the Speedstick? Have you heard of that? The first time I look at the thing, I was like, what in the world is that? Speedstick. What is the Speedstick? Have you seen this before? Do you know what they're used for? Make a guess. What do you think they're used for? Speedstick. Do you know what they're used for? After PE. After PE, they don't have that. Don't want to bathe, right? Very. Spray, then it's so stinky. Yeah, but that one is spray one. This one is stick. It's a piece of thing. It's like a cake. Not cake. It's like a what is that? It's like some kind of gel. Okay, it's not even a gel. It's like a stick. It's like a soap, piece of soap. They never show inside. So basically, you open the thing. Then where you put your armpit because smelly ma. After PE, very smelly, right? So you put there, put all, just roll over your body where you think got body odor. Okay, so does it get rid of body odor? No, you only mask the smell. Why? Because this thing is like, how does this look like? Speedstick. Is there? Can you see this? It's a cake of soap, right? Some kind of soapy thing. Then you just rub all over the body. Just rub over the body, right? So your body will now have like a layer of this cake thing. Then you got body heat, right? Body temperature cause this thing to sublime. So from solid become liquid. Why you don't want to put liquid? Because your clothing will become wet, right? So you don't want a wet look. You want a dry look. And then this thing sublime. So your friend will be, oh, Elijah is not so nice. But actually, this thing masks the body odor. The friend is still smelling the body odor. It's just that this one is more powerful than the body odor. Okay, it's called a Speedstick. They have so many. Are there? Look at that. They have so many flavors. Right? What flavor? Regular. What else? Lady also have. Lady Speedstick. Unstoppable. What is this? Put already, the guy will be attracted. Oh, so pretty, right? Then it smells like, oh, so pretty. Can you be my girlfriend? Kind of thing. Okay, so the idea is that it's dry. It's not sticky, wet. Yeah, that's what it is about. You can buy them, right, in the everywhere. Okay, NTUC, everything. So of course, another type is air refreshener, right? Not the spray, right? Refreshener gel. Those jelly type. It's like gel, right? They open the thing, then at room temperature, what happens? They become smaller and smaller. Okay, so I don't encourage putting this stuff. You know, some people really love to buy and put it somewhere, right? But don't forget, we are basically breathing the whole thing. Worse if you put in your room. Breathe. When you see this thing disappear, right? You know where it went? Yeah, go inside your lungs, you know. You might as well open and put it inside. The whole thing just slowly disappear. Then you, oh, I need to buy a new shipment of this thing, right? Where did it go? It went into your lungs, man. Okay, so disgusting, right? But of course, I know it smells nice. China one, cone gel. I know it smells nice, okay? And all these pebbles and whatever stuff, right? So sublimation, skip from solid to gaseous state. That's it. Okay. Is there a reverse from gas to solid? Actually, it has, right? It's a weird name. I don't remember what's the name. And opposite of sublimation, what's it called? Deposition. Solid to gas is sublimation. Gas to solid is called deposition. Right? No need to know. Okay. This. What's the opposite of sublimation? Advantage, A, liberation, assistance. What? Thesaurus. Wait, what? I don't understand. Oh, this English word. The English word of what does sublimation mean? Maybe it's an English word. Poo poo. I don't understand. It's okay. You see, English so troublesome, man. Science is so straightforward, right? It's just from here to here. Okay, so reverse is called poo poo. No, I'm not gonna write that. Poo poo. Deposition. Okay, so very simple. What's left to do is just 3 pages of MCQ. Okay, can you give it a try? So let's go through them. First one, a substance consists of particles that are close together, moving past at random average speed. It's gradually increasing. Liquid being heated. Okay, because the particles are close and moving past each other at random, it should be B. You get B? 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 Yeah, good. Next. What happens to the mass, volume, density? Mass stays the same. Volume increase. Density go to mass divided by volume. Yeah, B is correct. Only 2 MCQ. Okay, so describe what happens to the molecules in water as its temperature rises. So there are 2 things, right? You want to talk about the movement. So in terms of movement, what happens? They start to slide against each other at a faster rate. Right. So, but this thing is that it still haven't reached the boiling point, or maybe it can, you know, until it reaches the boiling point. How about the arrangement? What's the arrangement like? It's still disorderly arrangement, random motion. Okay. Still in the disorderly. Right. Disorderly arrangement, okay, random motion. So you want to describe, when they say describe, right, you describe in terms of the movement, the arrangement. Okay, this is temperature increasing. I haven't gone to the gaseous state. Thanks. By considering molecules in ice and water, why the density of ice is less than the density of water? How come the density of ice is less than the density of water? Do you know why? Ice floats, right, in the drink. So the reason why it floats is because the density is less than water. But why is the density less? That's a question. Any idea? You wrote something, right? What do you think? He gets what? Gets what, sorry? Oh, no. It doesn't get smaller. The volume increases. Volume versus water. Okay. So liquid water moving around, right? Can you see that they're pretty packed? Okay, even though there are some space in between, but they are quite close together, side by side. But frozen water looks like that. right? Orderly arrangement. Okay, the only problem is that there's a big spaces in between them. So the big spaces causes the volume to increase. So to answer this question, right, the molecules in ice form in a structure such that volume increases, hence the density. Okay, is the structure of this liquid. In the liquid state, they are very close together, but once they become the solid state, right, they form in this weird, this orderly pattern, which increases the volume. Hence, it will float in water. That's all. Okay, so you gotta say that the volume increased. Because if the volume doesn't increase, the density will not decrease. So that's that. So this is the reason why you should never put your Coke bottle in the freezer. Have you done that before? Really? Have you put a Coke bottle or Pepsi bottle? No? Okay, I have, right? So the thing it won't explode, but it will burst out, right? Like a Coke bottle in freezer. When I was young, I wanted like really cold. This is what happens, right? The volume increases because of water, because the water freezes, right? When liquid freezes, they freeze into some kind of a structure. So it will just burst off. Right? I think it will just burst. It will just overflow. Right? Oh my God. What is this? This is glass, right? So the thing just overflows. Okay, in the yeah, the thing will just overflow. Right? Because the liquid, something like that. The liquid will increase in volume. Okay? So next one. So a smooth piston and a rigid piston. What is this? A smooth piston and rigid cylinder is resting horizontal. There is some air trap. Why the piston stays at the position shown? What? Air particles can. So that's why the piston stops. The smooth resting horizontally. There is some air trap. Equilibrium means not moving. So not moving. So weird. Okay, so the piston stays the position shown. They say in equilibrium, we got to use our force. Okay, the idea of force. So when, okay, over here, right, what is pushing it in? No human hand, okay? But what is pushing this thing? And okay, let's talk about inside. What's pushing it out? The pressure in the trapped air. Now remember gaseous particles, what are they doing? They are flying over the place. So when they're flying over the place, they're hitting against this thing, right? Hit and then rebound, hit and rebound. They just rebounds from everywhere, okay? The gaseous particle. So there's some kind of a force. Is that right? Pressure, ma. So there's some kind of force. But at the same time, we have atmosphere. This is called the atmosphere. We call it the atmospheric pressure. Do you know what's atmospheric pressure? Do you know what it means when we say atmospheric pressure? Any idea? Sorry? Within the air, very good. Okay, let me give you an example so you understand what I'm talking about. Okay, this is the Earth. You're standing here. Now, obviously, above us, right? There's a what is like covering our Earth? It's called the ozone layer. Have you heard about that? Definitely have, huh? So what's this ozone layer? It traps the gaseous particles within the atmosphere. So the gas doesn't leak into outer space, huh? You know what I mean? Right? So now What is on top of this fella? Is it nothing on top of this fella? Is there nothing? There is something, right? Okay, what is on top? Maybe gases, air. Air is matter, right? Because of my handwriting power, mother. Air is mother. Matter. So there's matter. That means there's gas on top. And gas takes up space, has, wait, what's the definition of matter? Anything that has mass and takes up space, which means there's weight as well. That means there's something pushing down on you if you are standing outside of the building, or even right now over here. There's something pushing on you, even though you can't feel it because you're used to it. Okay, this thing pushing on you is called atmospheric pressure. Now, how tall is the column of air? How tall is the atmosphere? It's Earth's atmosphere. Okay, so you're standing here. Mount Everest is here, is pretty high, pretty tall. You have about 100 kilometers of air. So your head is actually sustaining 100 kilometers worth of air. Your whole body is being crushed by 100 kilometers of air. And we don't feel it because we are used to it. If you take another alien from somewhere else, come here, the alien might crush if they're not used to this atmospheric pressure. Okay, so we got this 100 kilometer worth of air that's on top of all of us as we're moving. Okay, as we're moving. So that's called atmospheric pressure. Now, when this thing is here, this thing, it doesn't look like much, right? Like, no, where got people pushing? Nobody pushing. But don't forget, above this thing, there's atmospheric pressure. The atmosphere is pushing it in. Okay, so this question, why the piston stays at the position shown, is a very oversimplified question. What does it mean? That means it looks very innocent, but actually there's a lot of science behind this. Okay, so the reason why it stays in position is because the force pushing from inside the cylinder equal the force That's it. Why this one doesn't move is because the force here is equal to the force here. Net force equals 0. You understand? Remember the force chapter? Right, so net force 0, so this thing remains the same at this spot. So the next question is, so when you hit the cylinder, the piston will move to the right, eventually it stops at any position. Why? So how come when we hit this thing, it will move? So the reason is simple. This is easier to explain, right? It's because hitting the air increases the heat energy, which is converted to more kinetic energy. Air particles, they will push the faster particles piston right. Until the force is So basically the idea is you heat this thing, increases heat energy, converted to more kinetic energy for the particles. the faster particles will push the piston to the right until the force is now equal to the force from the atmospheric pressure, and therefore it will stop at a new position. That's it. Okay. Next one. Okay, empty biscuit thing is the describe what happens to the air particle when the thing is heated. Okay, it's the same as here. You get it? Right? When you heat the tin, the air particles increase in kinetic energy. And yeah, that's it. Why the lid is eventually pop up? Okay, so the force is now able to overcome the atmospheric pressure that is pushing down on the tin. That's one. Second thing is the friction. Okay, let me explain to you. Biscuit tin. This is my favorite biscuit. Lee Mickey. One of them, right? We're talking about this type, right? Probably this type. Oh, what? This is JPEG file. Okay, something like that, right? So there's a tin, the red color kind, this side, right? So there are two things keeping this thing closed. Number one is friction. Number two is atmospheric pressure. Okay, so which one is stronger? Is it the frictional force or the atmospheric pressure? It's the friction, the frictional force between the lid and the tin. So when you heat this thing, right, the air particles inside there generate enough heat energy, convert to kinetic energy. So the particles start to move faster. And as they're moving, they push against this tin. Now, as long as the force is more than the frictional force, this thing will pop. That's it. Okay? Right? So I'm not going to type out the whole thing, right? But you get the idea. That's good enough. Next one. Moving on. Why the size of balloon increases when more is blown? Oh my god. Why the size of balloon increase? Okay. Balloon, right? From when it's very small. So when there's not a lot of air particles inside. Remember gaseous particles, they are moving, right? High speed, high energy. So when you pump more gas into the thing, okay, like here, you pump more gas into the thing, there are more particles inside here. So as there are more particles inside here, the particles are in random motion, high speed. And what they're doing is they're banging against the wall of the balloon from the inside. So as you get more particles, more of them will bang on the walls like that. So over here, there are not so many, right? It's just a few. That's why the balloon is not so big, okay? When there's less air particles. But when now they have more air particles, they will now, exert more force on the surface of the inner surface of the balloon, and hence it gets bigger. Therefore, the balloon increases in size. Okay. All right, done. Simple. Okay, moving on. Move on next one. Okay, now for the next one, I also have to do some explanation. Okay, before we begin, this is the Kinetic. This is the. Have you all done this before? Conduction, convection, and radiation. Got do before? Got do before? Right. So I just do a quick explanation. Okay. Conduction. Okay, so convection, conduction, and radiation. So these are the ways in which heat is being transferred from one place to another. So primary school we did learn, right, that heat is always transmitted from hot to cold. It's always hot to cold. So these are the three ways. First one, let's talk about conduction. So here's an experiment. You heat this part of the metal rod, heat will be transferred from the hotter part to the colder part. So eventually the hand will feel the heat. So in terms of the kinetic particle theory, what's happening here is, so what's happening here is that when you heat the particles, let's talk about conduction. We're going to see a picture of the particles. So when you heat the particles, so this is the metal rod. The metal rod. You heat the particles here. At first, they are just vibrating about the fixed position. But once they gain heat energy, they gain kinetic energy, and they start to vibrate more. Can you see now they're vibrating more? Right now, the vibration here, the vigorous vibration here, will cause vibration to its neighbors that are not moving, right? And once it gets enough kinetic energy, it will just be transmitted to the neighbors, right? Eventually, your hand or finger is here, you'll be able to feel the vibration of the particle, right? So what does this tell you about heat? Whenever you feel that something is hot, it's only the vibration. Okay, your fingertips is only feeling the vibration. It's just that the sensors on your fingers, right, goes all the way to the brain and tell you that, hey, your fingers, Mr. Elijah, your finger, you're vibrating abnormally. And then your brain is like, let me think. Maybe it's very hot, right? And then after that, they'll give you the information. Oh, this is called hot. Okay, and then eventually you decide, should I continue to put my finger there or should I remove it? Right? So vibration is the science behind you feeling heat. One more time. Vibration of particles is the science behind you feeling heat. So everything that is hot basically is just vibrating at a faster rate than it is normally. Okay? Like when you have fever, what happens to the body temperature? Increases, right? Temperature go up. Remember we say heat, vibrate more. You feel your forehead, you take the temperature thermometer of this. Suddenly the temperature higher. What does it mean? That means your whole body is like vibrating at a faster rate than what it should be. Okay? Right? So this is just heat transfer through conduction. So now you just have to be able to describe in more detailed form. Next one. Okay, wait. So let me go back there. So what about things that are poor conductors of heat? Why are some things poor conductor of heat? Where's the picture again? Conduction. Why are things like styrofoam poor conductors of heat? Based on this diagram. Conduct heat must like that, So how about styrofoam? How come styrofoam is a poor conductor of heat? Yes, Jovan. Yeah, very good. The distance has increased due to what? Air particles inside. So this styrofoam has got a lot of air particles inside that increases the distance between the particles, right? So that the vibration takes longer, or it's very difficult for the vibration to be transmitted from one end to another. Okay, let's take a look at styrofoam microscope. Yeah, all right, can you see that? So this is how a styrofoam particle looks like, right? Within the styrofoam under microscope. Shaving styrofoam. Right, so there are a lot of what? Air spaces. Okay, so the air spaces cause the heat, the particle to not be able to vibrate, pass. That's all. So that's why styrofoam is a very poor conductor of heat. Now we say poor conductor, it's not a non-conductor. It can still transmit heat because there are still some particles that are connected. Okay, there's still a few, that are connected. It's just that they're not so tiny together. Okay. Okay, next one, convection. So convection is a movement of heat through the movement of the particle itself. This one, right, so this is convection. So what happens in convection is that when you hit the bottom here, the hot water rises. Now, how come the hot water will rise? It's got to do with the density, right? So when here is heated, the volume increases. When volume increase, density decrease. So density decrease, it will rise, and you push the cold water downwards to be heated again. Then the hot water will rise again, and down and down and down and down. So the movement of the particle itself, causes convection, and the entire pot to be cooked. So users of convection are aircon. I mean convection. Okay. Where's the aircon? Cold. Okay. So why aircon must be at the top? Why? Why must be at the top? Because cold air will sink, and then warm air will rise. Okay, you'll be absorbed through the top. You ever seen the top of aircon before? Remember? You know what it looks like? Top aircon. No, you're not really sure, right? So the top is actually a lot of air vents, right? The top here, right, is full of air vents because it absorbs the hot air. Yeah, right. So hot air goes in, cold air comes out from the bottom. So hot air goes in, then cold air comes out. So this way it creates a convection current. Right. So we need convection current for this air conditioner to work. Right. So it's pretty easy. This is the reverse, right? This is warm air. What else? Okay. Next one, radiation. Heat transfer. Right, so this is the easiest example of radiation. If you have some campfire here, you feel the heat. Have you ever been to campfire before? Like real campfire, you know? Very hot, right? It's really hot, no? It's not so. At first I didn't think it would be so hot, right? But the campfire that I saw when I was in secondary school, it was like super hot. Army also tried before, right? Super hot, right? The amount of heat is just crazy, ridiculous, right? So radiation. So the heat can also travel through radiation. Now this is in the form of waves. It's in the form of waves, okay? Waves. So what this means is that anything that is hot will create heat waves that goes out from hot to cold. Now this wave will be amplified if someone is wearing like black color. Okay. No, black color. So if someone wears like a black color kind of shirt, they will absorb more heat. They will also radiate more heat. Okay, white color, they don't absorb so much heat. They also don't radiate so much heat. Right? That's the idea. So this one, black color absorbs heat. This one reflects heat. Okay, that's all radiation. So it's pretty simple. So, come back here. Okay, since you have gone through this, so I don't need to go through in details. Let's just try some. Maybe I think we can do some MCQ. Okay, let's go.